Now we're going to talk about the NOR circuit and the OR circuit. So we're working on digital logic. We've talked about the transistor and the NOT circuit. And then we talked about the NAND circuit and AND circuit. So in the first case, the NOT circuit, we had one transistor. And it reverses the input and the output. Next, we did the AND circuit and NAND circuit, which involved two transistors in series. And now we're putting two transistors in parallel. So let's see what this does. Now, if we put high voltage on here, meaning 5 volts, if we connect the wire up there, then that means this will be a closed switch and current can flow there. Likewise, if we put B up to the 5 volts, current can flow there. Now, will current flow through the resistor? It will if either one of these runs, or both. So if A is closed or B is closed so that current can flow, you will get current through there. And when that means you have connected X to 0 volts. So if either one of these is a 1, X will be 0. And if both of them are 1s, X will be 0. So the four possibilities again are 0, 0, 0, 1, 1, 0, 1, 1. Those are all the possible inputs. We can choose A to connect here or here. We can choose B to connect here or here. That's 4 options. So if A or B is a 1, that will connect us to 0. And X will be connected to 0. So if we have any 1s, X will be 0. Well, what if both of these are connected to 0? Well, then these switches are open. X is not connected to 0 volts in that case, and there's no path for current. If there's no current, there's no delta V. If there's no delta V, there's no difference between the X and the 5 volts, so X is 5 volts. X is a 1. And this is referred to as a NOR circuit. Because X will only be a 1 if neither A nor B is a 1. So let's make the modification, just like we did with the NAND circuit to turn it into an AND. Let's attach a NOT circuit. Let's chain these circuits together. So let's create another circuit here with an output Y, and the input's going to be X. So we know that if X is high volts, this will be a current, and this will be connected, and Y will be 0. So if X is 1, Y is 0. Meanwhile, if X is 0, this is open, there's no current. There's no current, there's no voltage difference, and Y is 5 volts, Y is a 1. So if X is 0, Y is 1, and if X is 1, Y is 0. That's what a NOT circuit does. And you can make a NOT circuit with a single transistor. So just like with the NAND becoming AND, the opposite of X is 0, 1, 1, 1. And so this full circuit with A and B as input and Y as output is an OR circuit. And to be specific, it's what we call an inclusive OR. If A or B or both are a 1, then Y will be a 1. So we say that Y is A or B. And we say X is A nor B, which is the same thing as saying not A or B. And again, that's not just means something else, that means specifically the exact opposite of OR. And so that is the basic idea of an OR circuit and a NOR circuit. And with the NOT circuit, the AND circuit, and the OR circuit, you can wire together an entire computer. So the OR gate symbol is a lot like the AND symbol, except this is curved, not straight. And so we have the output here, so this would be A and B and Y. In contrast, if you want to say a NOR circuit, you put a little circle here on the output. Likewise, as I said before, the AND circuit is symbolized like that, and the NAND would have a little circle there. A, NAND, B. And those are the extreme basics of digital logic circuits.